Hello students. So, in the previous class we concluded the part where we saw how vector calculus can be applicable to mechanics or applied mathematics, and there we derived several equations of motion for particles under certain laws of physics, and we also derived formulas for momentum, angular momentum, and things like that. So, now we are at a stage that we can move to the integral part of the vector calculus, which is basically the line integral, surface integral, and volume integral, and they basically include Green's theorem, Gauss theorem, and Stokes theorem. So, we will also learn about these three important theorems of vector calculus. So, today we are going to start with line integral. So, basically in vector calculus, any integral along a curve is called as a line integral in a nutshell actually. So, to start with, we will start with line integrals. So, any integral which is to be evaluated, along a curve is called a line integral, So, basically we know that equation of a curve. So, suppose the equation of the curve is given by R t is equals to f t, which is equals to basically x t I. So, three components x t I, y t j plus z t k be the given equation of the curve, and suppose we are integrating. So, suppose we are integrating be the given equation of the curve joining 2 points. So, 2 points which are, let us say A at t equals to t 1, and the second point is B at t equals to t 2. So, since these are obvious, I am not drawing any figure, all right. And suppose we have a capital F. So, we have a capital F which is a function of x, y, and z, and it is given as a capital F 1 x, y, z I plus a capital F 2 f y x, y, z j plus capital F 3 x, y, z k. So, these are all functions of x, y, and z, all right. Now, we are evaluating this function. So, suppose this is a function, is a vector function, defined and continuous along C, and if small s denotes the arc length, of the curve C, then dr ds, as we know, is the unit tangent vector, then dr dst is the unit tangent vector to the curve C, at the point P whose position vector is r, at a point P whose position vector is r, and then the component of f along the tangent is f dot dr ds. So, this is the component, and the integral basically, and the integral of this component of f along C from A to B is given by, so basically we integrate from A to B f dot dr ds. So, basically this here times ds. So, we are integrating along the arc length, and this can be written as integral from A to B f dot dr, and if we want to write in terms of the in terms of t, then we can be able to write this as integral t running from t1 to t2 f dot dr dt times dt. So, basically the point A is attained at the point at t is equals to t1, and the point B is attained at t is equals to t2. So, we divide both sides by dt, and so we divide sorry, not both sides, we divide this dr by dt, and we multiply it by dt, and then that is basically your integral of this f dot dr dt. We can also write it as a Cartesian in the Cartesian form. So, this one will be f1 times dx dt plus f2 times dy dt plus f3 times dz dt times dt. So, this is the required integral of this function f dot dr ds along the point from the point A to B. So, in this case we are actually integrating along a curve. So, C is the given curve, and which can be smooth or which can be piecewise smooth. So, when it is piecewise smooth, then we integrate along the one piece, then we integrate along the second piece. So, like in part we can do the integration. So, this is what we mean by line integral along a curve. And when we talk about, so there is a small definition here. So, in the line integral we can also talk about circulation. So, what do we mean by circulation? So, if C is a simple curve, if C is a simple closed curve, that is, i.e., that is a curve which does not intersect itself anywhere. So, there is no looping there. So, it is not intersecting itself anywhere. Then the tangent line integral of f around C is called the circulation of f about C, and it is often denoted by this symbol, and we write it as f dot dr is equals to integral C f1 dx, f2 dy, f3 dz. So, this is the required definition of the circulation of f around the curve C. All right. So, now we will try to solve some examples on the line integral, because line integral makes more sense when you actually try solving some examples than learning about the theory. So, let us start with our first example. So, when we solve the examples, the concept will become even more clear. So, evaluate, the first example is evaluate integral over the curve C f dot dr, where our f x y z is basically where f x y. So, we are in 2D. So, f x y is equals to x square times I plus y cube times j, where and sorry, not where, and C is the arc of the parabola, y is equals to x square in x y plane. In x y plane from 0 0 to 1 1. So, basically here we have a vector function f, and we need to calculate the line integral of this function f along the curve C, where C is the arc of the parabola from 0 0 to 1 1. Now, here in this case, so basically if we want to draw the figure, then this is our x, this is our y 0, and that is our parabola touching the origin, and we have to calculate the line integral along 0 0 and then 1 1. So, along this arc. So, let us say O A O basically. So, along this arc we have to evaluate the line integral for this function f. So, now what we do, we form a parametric equation. So, that means we involve a parameter t, and we find the range for that parameter t, which will satisfy this parabolic equation. So, let x equals to t, and then y will be t square, and if r is the position vector of any point on C, then our R t can be written as x t I plus y t j, which is t I plus t square j, and t will be. So, when x is 0, t is 0, when y x is 1, t is 1. Similarly, when y is 0, t is 0, when y is 1, t is 1. So, basically t will be running from 0 to 1. All right. Now, we will calculate dr dt from here. So, our dr dt is I plus 2 t j. All right. So, we have got our dr dt. Thus, integral over the curve C f dot dr is equals to integral t running from 0 to 1. Our f will be, so along this curve we are integrating along this curve C. So, in that way x is basically our t square and y is basically our x is basically t and y is t square. Yeah. So, I mean I squared after. So, this is t square I plus t to the power 6 j times, I will make it dr dt. All right. So, I will make it dr dt. So, then in that case this will be 1 to 0 t square I plus t to the power 6 j dot product with dr dt, which is I plus 2 t j times dt. So, now we will take the dot product, and sorry, this one will be 0 to 1. Now, we take the dot product, and this will be integral from t running from 0 to 1 t plus 2 t to the power 7. So, t square plus 2 t to the power 7 dt, right. And when we integrate, then this will be t to the power 8 divided by 8 whole thing evaluated from 0 to 1. So, this will be 1 by 3 plus 1 by 4. So, that means 7 by 12. So, this is the required answer. So, when we integrate the given vector function f along this parabola from the point 0 0 to 1 1, that will be our required answer. So, you see when we are actually working out the example, you get to see what I actually mean by this line integral. So, it is not always a line, I mean it is not something like a straight line. So, when we say a line integral, that means we are integrating along some curve, which can be smooth, which can be piecewise smooth, which can be simple closed curve, things like that. So, these are the certain properties our curve can have, and based on that we can calculate the line integral. We will work out few more examples just to make the concept a bit more clear. So, now let us consider another example. So, if f x y equals to 3 x y times I minus y square j, then evaluate line integral f dot dr, where C is the curve in the x y plane, y is equals to 2 x square from 0 0 to 1 1. So, this example is also pretty much similar to the previous example. So, here the given equation is again a parabola. So, we have to assume x equals to t and y is equals to 2 and y is equals to then will be 2 t square, and at both of these 2 points the equation will satisfy. Therefore, t will run from 0 to 1 and from there just integrating like before will give you the required answer. So, this example is exactly like the previous example. So, I leave this example up to the students for them to practice. We will now move on to our next example, which is this one, example 3. So, the example 3 is evaluate C x dy minus y dx around the circle x square plus y square equals to 1. So, here the given equation of the curve, C is basically a circle x square plus y square equals to 1. So, this circle is actually a simple closed curve because it is not forming any kind of loop. So, it is not intersecting itself, it is actually a simple closed curve. So, this is nothing but the circulation of the function f. It is also very easy to get the function f from here. Let us see. So, the given equation of the circle is x square plus y square equals to 1. So, from here, from the equation of the curve, we have x equals to so basically the radius of the circle. So, radius is 1 obviously. So, we have cos t and y is equals to sin t, where t is running between 0 to 2 pi, because we have a closed circle. So, our t will be running from 0 to 2 pi, and this function here x dy minus y dx can be written as y minus y I plus x j dot product with dx I plus dy j, and this is nothing but f dot dr, where this is actually f and this is actually dr, right. And from here I can be able to write f dot dr dt times dt. So, this dr dt can be calculated very easily. So, dr dt is nothing but dx dt I plus dy dt j, which is minus sin t plus cos t. So, from here what we will obtain is Um, so, the equation of the curve can be written as, or can be given by R t equals to x t I plus y t j. So, x t is basically cos t I plus sin t j, right, and now we will take dr dt. So, dr dt is minus sin t I plus cos t j, all right. So, now I will do the integration. So, now we have integration over the curve c x dy minus y dx, which can also be written as integral over the curve c f dot dr dt. So, what is our f? F is minus y I, and y is sin t and x is cos t. So, we substitute these values. So, y is sin t and x is cos t, dot product with dr dt. So, dr dt is minus of sin t I plus cos t j. So, this is minus of sin t I plus cos t j times dt, and here t is running from 0 to 2 pi. So, we will take the dot product, and that will result into sin square t plus cos square t. So, ultimately the whole thing will be 1, and therefore, we will have integration of dt, which is something like this, right. And when we integrate, then we substitute the value, and then this is basically 2 pi. So, the circulation of the vector function f, which is given by this way, is actually equals to 2 pi along that circle C. So, sometimes you are not given the function f, and there you have to actually obtain the vector function f. So, it is also a little bit small trick, it is not actually complicated, it is very easy to see what can be our function f be. So, just have a look at the given given integral, and from there you can be able to evaluate, okay, this will be my vector function f, which I need to take a dot product with dr dt, and from the given equation of the curve, where you have to calculate the integral, you can be able to find out the equation of the curve in vector form, and then you calculate dr dt, and then the rest of the things are same as the example 1. So, like we did in this example. So, we calculated the circulation of the function f, which was not given. So, we calculated the vector function f along the given curve C. All right. So, we can have examples similar to this, many examples similar to this actually. So, I am just looking into my lecture note, which one to consider. Now, what we will do, let us consider this example. So, here in this example, example 4 I believe. So, evaluate f dot dr, where f x y z is basically x y I plus y z j plus z x k, and the given curve is r is equals to t I plus t square j plus t cube k, where t runs from -1 to +1. Now, this is not a very complicated example. So, from the given equation of the curve, which is this one, we can be able to obtain our x t, which is t, our y t, which is t square, and our z t, which is t cube. And then we substitute x t, y t and z, then we substitute x t, y t and this z t basically in this equation, and we do dr dt, and then we calculate dr dt from here, and then we substitute the value of dr dt and we integrate from -1 to +1. So, here in this example it's just that the equation vector, I mean how to say, in the Cartesian form x t, y t and z t, the equation of the curve is not given, but the vector equation of the curve is given. So, from there extracting x t, y t and z t is relatively simple. So, here we see that in this example you can actually be able to write x t, y t and z t, although they are not given. So, you see these examples, I mean one thing is not given, then you can be able to obtain the other thing. Similarly, the other thing is given, then you can be able to obtain the first thing. So, it is all about doing practice and getting used to the examples of this type. They are not complicated, they are just playing with some parameters. That's pretty much it. And from here on onwards, you can be able to solve this example very easily. Just substitute these values, here, do the dr dt from here and then integrate from -1 to +1, and then everything is like piece of cake. All right. So, this is also very simple, yet how to say, a nice example. Next, I am going to consider an example which is I personally like. So, here we have to evaluate like before f dot dr, where our given vector function f x y is x square plus y square times I minus 2 x y j, where C is the curve, where C is the rectangle in the x y plane. X equals to a, y is equals to 0, x equals to a, y is equals to b, and x equals to 0. So, the solution. So, here as you can see we have a rectangle. So, obviously, it is not a smooth curve, because then you have 4 corners here. So, if I draw this curve, so that is our x axis, this is origin, this is y axis. So, this is my x equals to 0 line, this is x equals to a, and that is y is equals to 0, and that is y equals to b. So, I can write it as a, b, c. So, this is our curve, right, not the middle portion, the curve, this one. All right. So, now it depends on us which direction are we following. Are we calculating in this direction or are we calculating in this direction? So, that is one thing. Now, the second thing is that whatever we get along this direction, we just have to take the reverse direction actually when we are on the upper side. All right. So, this is a very interesting example, and we will actually try to solve this in our next class, because it will require some time to see the interesting part of this example. So, I will stop here for today, and in the next class we will continue with this example, and I thank you for your attention, and I look forward to your next class.